this lecture, we're going to start with two-dimensional flows. In particular, we'll start with linear two-dimensional flows. So what do we mean by linear flows? So in one-dimensional flows, we had something of this form. So x dot is some nonlinear function of x. I mean, this is an autonomous equation, and when fx is linear, that is fx is of the form x or c1x, then this equation is a linear equation. What do we mean by linear 2D flows? So two-dimensional flows, first of all, we must have x dot equal to some function of x and y, and y dot is equal to some other function of x and y. So this essentially encompasses two-dimensional flows. Now when fx, y and gxy are linear functions of x and y, meaning x dot is some c1x plus c2y, or more generally we can say x dot is ax plus by and y dot is cx plus dy, then such kinds of flows are called as linear flows. And the reason why we study linear flows is that the behavior of linear flows will give us more insight into the behavior of non-linear flows. It holds the key towards understanding what the behavior near various fixed points will be. And I reiterate the fact, this is not a theoretical course on nonlinear dynamics, but regardless of that, by pure geometry, we'll try to make use of Python, and the equivalent script in Octave will be also up on my website. So how we can use these tools to visualize and understand the basic idea behind interpreting such kinds of equations. Once we have cast the equation in this linear form, we can then write this equation down in a matrix form. So x vector is the vector xy, and so x vector dot is some matrix times x vector. In this particular case, the A matrix will be this: A, B, C, D. And whenever there are matrices involved, we can bet that the eigenvalues and the eigenvectors have something to do with how this system of equations, this dual system of equations, fundamentally behaves. Because the eigenvalues and eigenvectors hold the key towards unraveling the structure of a set of equations which is sort of bounded together or mapped by a matrix. So essentially, we are mapping this state with the rate of change through this kind of a matrix. All right. So let us consider the very simple linear equation, and the linear equation in this case will be a simple harmonic oscillator. So what is the governing equation for that? So mx double dot plus omega square x, or not omega square x, this will be kx, is equal to 0. Okay, so this particular equation is what governs the motion of, so if this distance is x from this, the spring constant is k, the mass of the block is m, this equation governs how x changes in time. Now this is a second order differential equation. We can cast it in the form of two first order differential equations. Okay, so the first task will be to split this equation into two first order equations. So let v be equal to x dot, and consequently v dot, which is essentially x double dot. Okay, so this is what the basic substitution will be. So if v is equal to x dot, we can write mv dot is equal to minus kx, or essentially v dot is equal to minus k upon m x, where k upon m we can we can, I mean, if you remember your high school physics, k by m is like the omega squared parameter of an oscillator. Okay, we're not going to discuss about how this comes into being, but it's related to the frequency of oscillations. So v dot becomes minus omega square x. So thus we have two equations. So x dot is equal to v and v dot equal to minus omega square x. In the case of one-dimensional equations, we had an idea of a vector flow, and the vector flow simply told us on a one-dimensional line how does a point move and the motion of the point was dictated by the velocity or x dot corresponding to this particular location. So if x dot at this location is positive, this particle will tend to move towards the right. If x dot is negative, it will move towards the left. So the vector flow in 1D showed us how points would move on a line, and from that we were able to see whether various points on the line would be attracted towards a certain point on the number line, or it would be repelled away from a certain point. But in 2D, we have now two dimensions to play with. So we have both x and y, and at a given collection of x and y, there will be two velocities, x dot and y dot. In this particular case, it will be x on the x-axis and v on the other axis. Okay, so x dot and v dot are like telling us how this point in this plane would move given this kind of flow. So this is called as a 2D flow, and depending on this, the right hand side, it would tell us how this point would move. If at a certain x and y, x dot is positive and v dot is also positive, then obviously this point will tend to go towards a higher x and a higher v. If at this point x dot is negative but v dot is positive, then the motion would be something like this. It would go towards a lower value of x and a higher value of v. So such kinds of diagrams are called as phase portraits, and they tell us how various points in the two-dimensional abstract plane, in this case x and v, would move in response to this right hand side. Now, while this information is very useful, the reality is you will solve this to obtain x as a function of time and v as a function of time, and then you will plot, you will have a time series of x, how it will vary, and v, how it will vary. But here we are not so much bothered about the time it takes, but we are more bothered about the overall behavior of the system, and it will be clear through examples. So essentially we are parameterizing these time series with the help of this two-dimensional plot. Here the time no longer comes into picture. Okay, it is just the trajectory in the phase space. It could look something like this, or it could look something like this, okay, depending on what this right hand side function is. But we don't know how much time it might have taken for it to reach this phase point. So phase point in this 2D plane is a combination of x and v, which the particle might have reached or the particle might have originated as well. So for all the points on the two-dimensional plot, we can sort of find a trajectory. So these kind of curves are also called as trajectories. And this trajectory, it tells us what phase points the curve passes through in order to reach at some equilibrium, or whether it goes on forever. There can be various conditions, and we are more interested in how those conditions are rather than the time series. Of course, the time series is very important to understand the time taken for a certain motion. Okay, so let us try to first have a qualitative understanding of how this flow would look like. In order to do that, we go to our console. Let me just copy this. We'll require this in our lecture. We don't need fsolve, so we'll get rid of this, but we will eventually need solve IVP. So from scipy dot integrate import solve underscore IVP. So let me execute this. All right. So in order to find out the flow, let us do the following. Let us define first the two-dimensional phase space. So let me show what I'm trying to do over here. So essentially, we will choose all the values of x and all the values of v. We'll make a linspace. Then we'll convert it into a mesh grid. Okay. The first point is to make a linspace. Then to make a mesh grid. Once we have that, for all the points in the xv plane, we will see how the x dot and v dot look like. So the x dot and v dot are like the x velocity and the y velocity for this particular 2D plot. If you recall, x dot will be equal to v and v dot will be minus omega square x. So we would like to see how the vector points, okay, at each point in the domain. So let us do that. So let me go over here and say x equal to np dot linspace, say minus 3 to 3, y or v equal to np dot linspace minus 3 to 3, x comma v equal to np dot lins mesh grid x comma v. Now once we have this, let us define. So let me call this as u and v. I mean, that's very convenient. Let me call this as capital U. Let me call this as capital V. So it's like the velocities in the x and y directions respectively. So we will define the function. So u is simply equal to v. Yes, u is we have already used v. Okay, let me call this as w. Rather, let this be v, and let me call this as w. So I'm calling it as u and w because we have already used the capital V variable. And v will be equal to minus omega square times x. Okay, so these are the definitions. We have to define omega. So let omega be equal to 1. No problem. Alright, let us execute this and see if there's some error. Okay, v is undefined. Obviously, this has to be w. Alright, so now we are in a position to make a plot of how the vectors look like. So we'll say plt dot quiver x comma w comma u comma v. I've messed it all up. As per the convention over here, this should be v and this should be w. Okay, so let's not confuse this anymore. I'm using the same convention that I've written in the notepad. So there's too many arrows for us to see what's going on. Let me reduce the density of arrows. Let me just take 20 points over here. Okay, so we have plotted in the xv plane how the velocities look like. So let us look carefully what is going on. So we have the origin over here where the arrow lengths are quite small, and it means at the origin the velocity is very close to 0. Let me just set the aspect ratio properly. So plt dot ax equal to plt dot gca, get current axis, ax dot set aspect 1. Alright, so at the origin, what do we have? So at the origin, so x will be 0, v will be 0, and correspondingly u will be 0 and w will be 0. So the x velocity is also 0, so the w velocity is also 0, and this is obviously a fixed point. So the arrow lengths are going to 0 over here. Now let us look at a positive value of v. So let this be the origin. So a positive value of v and x equal to 0. So over here x is 0 and v is positive. So when x is 0 and v is positive, the v dot is 0. So x 0, v is positive. So v dot is equal to 0 and u dot, or rather x dot, is some positive number. So the velocity is like this over here. By the same logic, when we have v negative, the velocity will be something like this. Over at this point, so at this point x will be positive and v will be 0. So when we substitute this, this results in x dot equal to 0 and v dot equal to negative. Okay, it's minus omega square times x. So the velocity will look something like this, and by the same logic something like this. So we see that if we had an initial condition over here, the particle would be pushed like this all the way to here. The particle would be pushed like this, it would be pushed like this. So this is how the particle trajectory is expected to look like. Now, yeah, I mean, you can sort of see that how everything is trying to go in circles. All right, but can we find out that particular curve? Okay, how do you find out what this curve is going to be? Let us see. Let us start with this equation. So we have x dot is equal to v and v dot is equal to minus omega square x, and this implies dx dt is equal to v and dv dt is equal to minus omega square x. Let us divide this. So we have dx upon dv is equal to minus v upon omega square x, and thus omega square x dx equal to minus v dv. Let us integrate this. So we have omega square x square upon 2 is equal to minus v square upon 2 plus some constant, and actually we can write this as omega square x square plus v square is equal to some other constant k. Now what is the value of the constant? It depends on the initial condition. If we choose x naught equal to say k1 and v naught equal to k2, then we have omega square x square plus v square is equal to omega square k1 square plus omega square plus k2 square. So depending on what the initial conditions are, we are essentially setting this function's ISO value. So now it all boils down to finding out the ISO values of this particular implicit function. Essentially, we've landed up with a situation where we need to do an implicit plot. So let us go ahead and do that. Let me go to this curve over here, this code over here. Let me define x1 as np.linspace -3 to 3. Let me take more points. v1 equal to np.linspace -3 to 3, 100. Now we will have capital X1 v1 equal to np.meshGrid x1 comma v1. Then we will define a function capital F as omega square times x1 plus x1 square actually plus v1 squared, and we need to plot. So essentially the function on the left hand side, this is f. So f is omega square x square plus v square. And now depending on which ISO value of f we plot, we should obtain various contours corresponding each to a different initial condition. Alright, so let me go ahead and plot this. So plt dot plot, not plot but contour. We will make a contour in the x1 v1 plane of the function f and levels equal to LVL. Let me define what LVL is. So it's, say we define a bunch of levels starting from 0.1 all the way to, so the domain is extending from -3 to 3. Alright, so the domain actually extends from -3 to 3. So this point is going to be 3 comma 0, and omega is equal to 1, or rather let us see what the maximum value will be. So it will be omega square times 3 plus 0. Okay, so the maximum value of this function in the domain that we are plotting in, it will be omega square times 9 plus 0. So let us take levels, so LVL varying from 0.1 to 9. Let me not hard code that 9 as well. So let me just say np dot max of x1 squared times omega squared. Okay, so I have not hard coded anything, because if I change the domain, I should still be able to plot the good ISO levels. Okay, so better not to hard code anything, or rather to minimize hard coding. All right. Okay, so let us run this. Okay, there's an error. NumPy has no attribute in space. Where is it? Which line is it? We have written lin pace, so it should be lin space. Okay, so there's too many ISO values over here. Let me reduce the number of ISO values. So we will take only, say, 6 ISO values. Great. So these are the ISO values. All right, and the arrows actually indicate how the flow is looking like, and the closed orbits. Okay, so this particular curve that we had predicted, it's going to be a closed orbit, and this is the fixed point. Okay, so this is the simple harmonic oscillator in the phase space. Now can we interpret this? Can we interpret this plot? So what's going on? We have a closed contour like this, okay, and the arrows seem to go like this. Okay, so let me try to interpret it. So if we start off at a point over here, so what does this mean? So this is, if I reiterate, this is x comma v. So x value is 0 over here, but v has some positive value. Say that it has a value of a. It means that if I take the spring mass system, it is the equilibrium configuration. Okay, so x is 0 over here and x can go negative. It means that the spring will compress, and if x becomes positive, it means that the spring will elongate. So x equal to 0 is like a situation where the spring is not tensed or not compressed. And now a positive value of v means I'm imparting a certain velocity in the positive x direction. I'm imparting a velocity in this direction. So what will happen when you imparted a velocity? The x value will increase. So we are moving towards this. So the x value has increased. So if we plot the velocity, so we see that the velocity has reduced. Okay, it's reducing. But if we simultaneously plot the x, okay, so it's increasing, and it will go all the way to this point. At this point, what do we have? We have some positive value of x and the velocity becomes 0. So this particular point, it corresponds to the case where the block has gone all the way to the end, where the spring is now at its maximum elongation. The mass decelerates and reaches the maximum farthest point, at which point the velocity becomes 0 but x is maximum. So over here we have the maximum value of x and the velocity 0. So something like this, and that corresponds to a 0 velocity, something like this. And then we see that x begins to reduce. Okay, so the x is now reducing as we go, and the velocity is becoming negative, meaning the block is now traveling in the negative x direction and the velocity is increasing. So this is how you can justify the presence of such closed trajectories. It goes all the way till it reaches the initial point, and this is a simple harmonic oscillator without any friction. Now, can you tell me what will happen if this particular system were to have friction losses? If we were to have friction losses, what would happen? Now, when the particle would go like this, or when the block would travel like this, at each point the block would be losing energy. So once it reaches the other symmetric point, so what is this point going to be? It's the point where we have maximum compression. But will we have the same velocity a that we had started with? And the answer is no, because due to friction, you're losing energy. So the velocity that the block will reach at the end, at the other point, that at the point of maximum compression, it would reduce. So we would have something like this, and it would go like this, and eventually you would reach a condition where the block has no velocity and it is at equilibrium. So this is the motion with friction. Okay, so I hope you can appreciate how we can visualize this, and it's let us see whether we can make a simple change to account for friction. How will friction appear in this equation? So in this equation that we have over here, there will be mx double dot plus cv plus kx. Okay, this will be equal to 0. So x dot will be still equal to v, and v dot will be minus omega square x plus some new constant, say c. Let's call the new constant also let me call it p to avoid any conflict, plus, or rather it would be minus p times v. Okay, so let's make this particular modification. Okay, so w will be minus p times v. Let me define p equal to 0.1, and let me remove this contour plot because that integration will not be exact. So let me remove it. Okay, let me remove it. So let me run this and let us see how the arrows look. Let me increase the value of p to something like 0.8. Now look how it starts to look more like a spiral. Okay, it looks more like a spiral, and it's slowly losing energy, and it will go to the origin. While we have obtained the analytical expression for the closed contour in the previous case by dividing the two equations and integrating by parameterizing time rather, we can also make use of the streamline plot in order to plot this particular trajectory for the dissipative case. Okay, when there is friction, we don't have an analytical solution per se, but even if we don't have an analytical solution, we can use this particular vector field to integrate numerically and find out how the trajectory will look like. So what is happening when we have done this particular thing? So dv dx is that was equal to minus omega square v upon x. This is tantamount to having an initial point somewhere and then integrating it and seeing how it goes. Okay, this is what we are essentially doing, and that we found out analytically. But instead of doing it analytically, we can also do it numerically. And NumPy, I mean even GNU plot, MATLAB, whatever, when we draw a streamline, plotting a streamline is tantamount to using that velocity field and finding out the trajectory in that velocity field. Even if the velocity field is time dependent, you freeze the velocity field and find out the trajectory on that frozen velocity field. So now I've brought back x1 v1. Let me copy the expression with friction over here, and let me substitute this by v1. This will be x1 and this will be v1. So the reason why I am having two different grids is I want to have the vector field with few points plotted. If I don't plot it with 20 points, if I plot it with 100 points, there's too many vector fields all over the place and we cannot discern anything useful. So I've kept the number of points on which the vector field is to be plotted quite low. On the other hand, things like the ISO contour or the ISO value or the contour or this particular streamline that we're going to plot, I want it to be on a refined mesh so that the curves appear to be smooth. That is the only reason why I'm using two different sets of meshes. Okay, there's no other reason. I could have very well used a same mesh. It would have made things very nasty. Nothing else. Okay, so when I define u1 as v1 and w1 as this, I can now call plt.stream plot x1 v1 u1 w1. So I will pass the velocities to it. In fact, let us just run this much and see what happens. Okay, it's giving us a bunch of streamlines, very broken streamlines, because it's plotting it using a uniform density, but we don't want that. We want the streamline or the trajectory to start from this particular specified point. So we will specify start points equal to so this will be two things. So we will start with x at 0 and y at say 2.5. Let us run this. Okay, there's an error. Not an okay. So I must declare this as a NumPy array. So seed points equal to np.array. So there has to be two sets of points. One will be 0 and one will be 2.5. Let me then pass seed points to it. There's still an error. Yeah, okay, so we must pass it as, I mean, these are some idiosyncrasies of Python again. Even if we create different initial points, so suppose there is one initial point at 0.5 and the velocity is 0, we must pass the transpose of that array. These are just small things that Python requires you to do. Obviously, the syntax will be different for the case of GNU Octave. Okay, so you have to pass the transpose of it, otherwise it's not able to figure out what you have passed. Okay, it's quite simple. So but now look what is going on. We have given this as the initial point, but it's giving us the forward contour and the backward contour, and the reason is obvious. Let us go to the contextual help of stream plot. there is something called as integration direction. Okay, it says both, but integration direction we want only in the forward direction. Okay, so let us go over here and change the integration direction to only forward, and this gives us the spiral. Okay, let me now increase the parameter which controls dissipation to 0.5. Let us see. Okay, so the thing quickly fizzles down to 0 as we had predicted. Okay, let me make it 0.8, so the two contours go to 0. Okay, so this is how you can plot a streamline and how you can visualize the vector flow for simple cases. So now let us move ahead to find out the behavior of a prototypical linear system. So x dot is equal to ax, where a is given as a 0 0 minus 1. Okay, so let us look at how this particular system would look like for a matrix which looks something like this. So when we have this, we can write dx dt is equal to ax and dy dt is equal to minus y. This is because x dot y dot will be equal to a 0 0 minus 1 x y. So once you do the multiplication, you will obtain this. So with this, we can divide these things and we can write dx upon dy is equal to ax, or rather minus ax by y, and so this becomes dx by x equal to minus a dy by y, and ln x plus a ln y is equal to constant, which means x times y raised to a is equal to constant. Okay, or alternately we can simply do a plot of this as well, do an implicit plot of this. So let me copy this particular code over here. Let me go over here and write down, so we don't need this, we will simply require a. We can put y over here. Okay, so u equal to a times x and v will be equal to minus y xy uv, and this will be also x1 y1, this will be y1. But instead of having the stream plot, we can make use of the iso function that we have obtained over here. So we can define f equal to np dot log of np dot abs of x. And the reason why I use absolute is because we are taking a log, plus a times np dot log of np dot abs of y. Okay, we don't need this, we don't need seed points, so we'll do simply plt dot contour x1 y1 comma f. So this has to be x1. Let me change the number of contours to 20. Okay, so when we want to study this equation, this particular equation for different values of a, let us keep a as a variable. So let us define a wrapping function because we want to make it interactive. So define effect of a, and the input will be a. Let the default value be equal to 1. Okay, we have to put everything over here inside the function. W equal to interactive effect of a. A will go from minus 1.5 to 1. 5 in steps of 0.05. Then we have to display the widget as well. Okay, so let me go to a value of minus 1.5. In fact, let us decrease the number of contours. So let us see what happens when a equal to minus 1.5. Okay, so a is minus 1.5. Let us see what the plot looks like. Let us look at this equation. So dx dt is minus 1.5 times x, and dy dt is going to be minus y. So this means that x is x naught e raised to minus 1.5 t. This implies y is y naught e raised to minus t. So x decays faster than y. Okay, so x decaying faster than y means if I have an initial point over here, the decay in the x direction will be faster than the decay in the y direction. Okay, so it will look something like this. Okay, so that is why we have the curves which look like this. In fact, let me make this minus 2 to make it more emphatic. Okay, this makes it more emphatic. It's something like this. Okay, so the y-axis also attracts and the x-axis also attracts. So if we choose a point on the x-axis, that is y equal to 0, the equation will be simply this, and the point will go towards the origin. If we choose simply the y-axis, that is x equal to 0, the point will also be attracted towards the origin. Therefore, the fixed point in this system, that is origin, is called as a stable node. So for a less than minus 1, it will be a stable node. Let us in fact now go to the case where a is minus 1. So what do we expect? Dx upon dt is minus x, and dy by dt is minus y. So both the x and y are sort of attracted towards the origin at the same rate. Okay, so at minus 1, so all the lines are coming towards the origin, and this particular case is called as a star. It means that all the points are coming towards the origin. The reason why you have these artifacts is because of the discretization of the mesh, nothing else. Okay, so let me increase this to 500. Let us see if that makes things better. So one is, yeah, that makes things slightly more aesthetically good. I mean, you can change all this by selecting certain levels of contours, but I'm not going to do that right now. You can do it when you have time. So this becomes a star. This means all the points in space are attracted towards the origin with an equal magnitude. So x is also reducing, y is also reducing. Over here, x was reducing faster than y, but here it is all attracting. So the fixed point is called as a star. It's also a stable fixed point. Now what about a greater than minus 1? Okay, see how the curves are bending. So when a is greater than 0.1, say a is 0.5, then dx dt becomes equal to 0.5x, while dy dt becomes equal to minus y. So x is attracting slower than y. So the trajectories are faster in the y direction and then slower in the x direction. So the trajectories travel towards the x-axis faster than in the y-axis. So hence the trajectories look something like this. Okay, it's moving faster along the y direction. It's just a swap of the initial case where a was less than minus 1. Okay, so the arrows also indicate the direction of the motion. Now let us see what happens at a equal to 0. So at a equal to 0, all the vectors are pointing towards the x-axis. So a equal to 0. Okay, so before that, this is also a stable point. Okay, all the points are being attracted towards the origin. So this is also a stable node or an attracting node, whatever you want to call it. At a equal to 0, this thing becomes 0, and so dx dt is equal to 0. Hence x is a constant. But dy dt is still minus y. So y things, the points along this axis, they converge towards x, and so the x-axis essentially becomes a whole line of attracting nodes. Okay, so this particular case is called as, it's like a marginal case. You had only one point, and then suddenly you have a infinite number of stable points. So it's like a marginal case, and so this line is called as a, I mean, it's a line of stable points. Okay, it's a line of fixed points, stable points. I mean, it's not a stable point, it's a line of fixed points. Now when a group becomes larger than 0, see what happens. Dx dt is some, say, 0.5 times x, and dy dt is minus y. So x is growing exponential in time. So if I have a point on the x-axis, it is growing exponential in time. So it is going away from the origin. But a point on the y-axis is nevertheless attracted towards the origin. Okay. So this particular fixed point is attracting in the y-axis, but repelling in the x-axis. So this kind of a fixed point is called as a saddle node, because the saddle, that you put on a horse, it has a curvature like this in one direction and a reverse curvature in the other direction. So it's attracting in one direction and repelling in the other direction. That's why it's called as a saddle node. Okay, something like this. So it's attracting in this direction but repelling in this direction. Okay, so you just imagine how a saddle of a horse looks like. Okay, so the points, when they start over here, they are attracted towards in the direction of y towards the origin, and they're repelled like this. Okay, so it's called a saddle node, and the important thing is, for t tends to infinity, the point is attracted towards the unstable axis. I mean, you would imagine that at time goes to infinity, it would be attracted towards a stable orbit, but no, toward a stable axis, but no. Here, it is attracted initially towards the origin in the y direction, but then once it becomes close to y equal to 0, it gets pulled away to infinity along the x-axis. So okay, so it's attracted towards the unstable axis. It sounds very counterintuitive, but this is what it is. Where points go like this, points go like this, and points go like this. Okay, this you can see over here as well. Okay, so this is what happens, and as a keeps on growing, it's the same thing. So as the value of a has changed, the entire behavior of the equations has changed from a stable node to a line of fixed points to something which repels. And obviously this has to do something with the eigenvalues. Okay, so for this particular system in which only diagonal terms are present, this is one eigenvalue and this is one eigenvalue. This is the x eigenvalue, this is the y eigenvalue. Okay, so we can interpret it like that also, and we'll do it after this. But before that, just a bit of terminology. There is something which is called as a Lyapunov stable orbit, and the meaning of Lyapunov stable means, if we have a point which originates, which is away at a certain distance from a fixed point, so if the point remains in the vicinity of the fixed point for all times greater than 0. I mean, for all large times. So t tends to infinity if the point remains bounded. So it does not have to actually come back to itself. So if the point remains bounded like this, then we say that the fixed point is Lyapunov stable. If the point is attracted towards the fixed point, so it goes to the fixed point, then the point is said to be attracting. So Lyapunov stable is not the same as an attracting point. Okay, a point can be attracting, meaning if I start with a point close to a fixed point over here, okay, the point may very well go like this and come to the fixed point. It can still attract it, but it is going a long distance before it is getting attracted. So it is not Lyapunov stable, but it is attracting. Okay, similarly, the point can simply meander around the fixed point. Okay, it will not grow out of bound, but it will simply meander around. And if it doesn't cross a certain threshold, I mean, that is in your hands. If it doesn't cross a certain threshold, then we say that the point is Lyapunov stable. So this fixed point is Lyapunov stable. Okay, so obviously this is not a course on nonlinear dynamics, but I'm just trying to throw these jargons over to you, so that when you do study it formally through one of these NPTEL courses, maybe you'll know how to go about it. It doesn't make a lot of difference for us to understand the tools that we can use to understand such systems. Okay, so with this out of the way, let us move on to the analysis of a general system. Let us consider, I mean, it will be clear what the ramifications are of the eigenvalues through this example. Let us consider this particular example. It's a very simple example, but it will bring to the picture what is going on. So consider this. Let this be a linear system. So now we want to solve this. Okay, so we would be looking for the eigenvalues of this system. So let us actually look into what the eigenvalues of this matrix are. So 1 minus lambda, 1, 4 minus 2 minus lambda. So the determinant of this will be 0. So when we have a matrix A, the eigenvalues are found using the determinant of A minus lambda I equal to 0. So I'm not going to discuss elaborately on this, but let us see. I'll just give a small proof towards the end. So 1 minus lambda minus of 2 plus lambda minus 4. So what is this going to be? Minus lambda square lambda minus 1 times lambda plus 2 minus 4. So lambda square plus lambda minus 6 equal to 0, which implies lambda plus 3, lambda minus 2 equal to 0. So lambda equal to minus 3 and lambda equal to 2. So when lambda equal to 2, what do we have? So when lambda equal to 2, what are the eigenvectors? So the eigenvectors are 1, 1, 4 minus 2, v1, v2 is equal to 2 times v1, v2. This implies v1 plus v2 is equal to 2v1 and 4v1 minus 2v2 equal to 2v2. So this implies v2 equal to v1, this first equation, and the second equation also implies v1 equal to v2. So the eigenvector will be 1, 1. So this is the eigenvector. So lambda 1 equal to 2, the eigenvector is 1, 1. When the eigenvector, when the eigenvalue is minus 3, so what do we have? 1, 1, 4 minus 2, v1, v2 is equal to minus 3 times v1, v2. This implies v1 plus v2 is equal to minus 3v1 and 4v1 minus 2v2 is equal to minus 3v2. This equation gives us v2 equal to minus 4v1 and this equation gives me what does it give? 4v1 equal to minus v2. Okay, so it's the same thing. This is good. So the eigenvector will be 1 comma minus 4. So in the two-dimensional plane, so these are not normalized eigenvectors. So anyway, so the 1 comma 1 eigenvector will point in this direction, and the 1 comma minus 4 eigenvector will point in this direction. Okay, and what is the meaning of an eigenvector? Here it will be clear. So an eigenvector means if this mapping, this particular matrix 1 1 4 minus 2 is applied on this direction, it simply leads to a scaling of that direction. Okay, it simply leads to a scaling of that direction. Similarly, when it is applied on this direction, that is 1 4 1 minus 2 times 1 comma minus 4, it also leads to a scaling in that direction. So these directions are not altered by the action of this linear transformation. Okay, so if I have a vector like this, then it will be twice of that vector because of that mapping. It means that if I have an initial point on this line, that initial point will move somewhere over here at the end of next time step, and it will move somewhere in the next time step like this. But this is minus 3, so if you have an initial vector like this, it will try to contract. Okay, it is shrinking rather than expanding because the eigenvalue was negative. So the point is attracted like this. So we can see that on these special directions, the points are attracted and the points are repelled. So this particular fixed point, obviously for a linear system, the origin is a fixed point. This fixed point is attracting along this eigen direction, or the eigenvector, and it is repelling along the other eigenvector. Okay, so x dot is equal to ax. Okay, so if we know that the space, the two-dimensional space has eigenvectors v1 v2, then it means that any vector in this space can be written in terms of a linear combination of these two vectors. So x can be written as c1 v1 plus c2 v2, and this vector is not a velocity vector or something like that. It is the pair of terms x comma y. That quantifies the vector in the xy plane. Don't be confused with a velocity vector over here. Okay, so now what about this? If this is true, I can represent any point as a linear combination of these two. All right, this is a linear combination of the eigenvectors. Then I can substitute this over here and say x dot is equal to a times c1 v1 plus c2 v2, and this becomes c1 a times v1 plus c2 a times v2. But by definition of being an eigenvector, a times v1 will be lambda times v1. Okay, so this will be c1 lambda times v1, lambda 1 v1, plus this will be c2 lambda 2 v2. But c1 v1 plus c2 v2 was the original vector, so this becomes equal to lambda, I mean, so we cannot represent this anymore because lambda 1 is distinct from lambda 2. Okay, so x dot is therefore dictated by the behavior of the eigen value and the eigenvector. We cannot simplify this anymore. Okay. So if we choose the initial point to be aligned with v1, okay, if the initial point only consists of this eigenvector, then x dot will be c1 lambda 1 v1. It will be only this term. I'm just choosing the initial point to lie on that eigen direction. This is that eigen direction, and I'm choosing the initial point to lie on that. And this means that I am going to increase this vector continuously along the same eigen direction. So in this particular case, this particular eigen direction had a positive eigenvector, and thus points on this would continuously move away from the origin, while this eigen direction had a negative eigenvalue, and hence the points would be continuously attracted towards the origin. And now we can sort of reconstruct the trajectories as they would look. They would look something like this. Okay, they would look something like this. So now let us go to a computer and actually see whether this is how the trajectories look like. So fine, let me. So I've plotted first the vector plot of this. Just have a look at the vector plot. The points over here are going like this. Let us go to our prediction. The points are going something like this. The points are actually going something like this. The points are headed like this, and so on. So now let us plot on top of this the various streamlines. Let me copy this bit of code. Oops. Oh, yeah. So let me. Alright, so I've plotted the streamlines as well. We don't need this cell anymore. So the streamline makes it apparent. The trajectories come like this and go away like this. The trajectories are flowing like this. Okay, this is that. The trajectories are flowing like this. Now let us superimpose on top of this the the two eigen directions. Okay, so plt dot plot. So the first line will be x equal to y. So x1 comma x1. Let me make this eigen direction as black. So because it's the unstable axis, we'll make it like this. So dotted as a broken line. And the other line, what is the direction? 1 comma minus 4. So it will be x1 comma minus 4 times x1. And let me put it by a solid line. Okay, so let us set the y limits. Plt dot y lim, and it will be from minus 3 to 3. Okay, so the solid line is the attracting eigen direction, the broken line is the repelling eigen direction. Okay, and in the language of nonlinear dynamics, the repelling direction is called as the unstable manifold, while the attracting direction is called as the stable manifold. And for long times, as time goes to infinity, points in the phase plane will be attracted towards the unstable manifold. And whatever we had arrived at, the conclusions that we had arrived at numeric with just intuition, we could verify all this over here as well. Okay, you can have a look at the various things inside the stream plot in order to make it look better. Okay, you can change the CMAP as well, the norms, line width, density. You can play around with various. Let me change the density. We don't need, say, 0.5. Okay, so this looks much cleaner, if you will. So this pretty much shows how the flows in the phase plane look like. Okay, so now I request you to have a close look at the homework because whatever you would need to undertake the assignment we have done in this particular lecture, and I request you to pay very close attention to some of the things that will be covered in the assignment. Okay, it will help you in appreciate the structure of the system of linear equations in a better manner. So with this we end this lecture over here. In the next lecture we'll begin with the analysis of a system which has complex eigenvalues, and then we'll see how we can evolve from there. With this, I say goodbye. Until then, farewell.